Hello everyone. This would be the presentation of our research and development project on load balancer filter based approach to enable distributed rate limiting to APIs. First, let us go over the background and motivation of our research. Let us begin with APIs. Essentially, they are mechanisms that allow software components to communicate with each other using a set of predefined definitions and protocols. APIs are now fundamental in building complex softwares and interconnected systems. They also play a critical role in modern businesses. According to recent trends, API consumption is also growing exponentially in the last few years. As the consumption of APIs grows exponentially, the complexity in managing them also increases. Our research focuses on rate limiting of APIs in the scope of API management. Rate limiting is essentially restricting the number of API requests a client can make within defined time periods like seconds or minutes. It's useful for various reasons, including mitigating denial of service attacks, ensuring fair resource allocation among clients. It enables a way for organizations to monetize their API services, and it is also used to detect and prevent API abuse, therefore maintaining the performance and preventing degradation under high loads. In modern architectures and scalable systems, APIs are being increasingly deployed across multiple geographically dispersed nodes, servers, and data centers. This is done for maintaining a high performance of APIs, ensuring fault tolerance, ensuring security, and also fairness. Modern applications increasingly rely on these distributed architectures to enhance the overall scalability, resilience, and enable geographic redundancy of their applications. Rate limiting in non-distributed deployments is relatively straightforward since we need to maintain the state only in a single node. However, in case of distributed deployments, as we discussed previously, it brings in a new set of challenges that needs to be solved. The first and foremost is a consistent state should be maintained across these multiple distributed nodes, and these states should be synchronized in a manner that does not affect the overall performance of the rate limiting system. Also, the rate limiting system should be able to scale with the increasing number of nodes or the API clients. Also, the rate limiting system should be fault tolerant and it should be resilient to node failures and should enforce the rate limits even in case of such a scenario. The approach that we will be going forward in this research to solve the distributed API rate limiting problem is to enforce this rate limit through distributed load balancers. Load balancers act as the centralized control for API traffic, so we could enforce consistent API policies. Load balancers are also naturally designed to scale and it could handle large volumes of traffic. It also eliminates the need for redundant communication between backend services or between external rate limiting systems since load balancer is already situated in the network path. It also provides a clear separation of concerns, separating the core application logic from the rate limiting logic. So ultimately, this research aims to solve the distributed API rate limiting problem by implementing and benchmarking various rate limiting algorithms and utilizing state synchronization methods within load balancers. The goal is to identify the most effective approach by evaluating performance under various experimental setups in a cloud deployment as well as a local deployment and further optimize for performance and better accuracy. Now, let us briefly go over the related works for our research. So, this is the overall summary of the literature review we have conducted for our research on both existing academic researches as well as on currently utilized industrial implementations. We have categorized existing academic researchers based on their scopes and the resources based on the rate limiting patterns. And we have also further classified the studied industrial implementation based on their point in the overall architecture of the system. This rate limiting could be implemented at endpoints such as on the client or server side, or it could be implemented somewhere in the middle in a middleware such as load balancers, API gateways, or proxy services. Each of these approaches have their own pros and cons. By doing this literature review and analysis, we were able to survey various algorithms that are being used to rate limit APIs based on the specific use cases and needs. The main algorithms are token bucket, leaky bucket, fixed window counter, sliding window locks, sliding window counter, and the generic cell rate algorithm, also known as GCRA. So, as a summary, existing research on API rate limiting mainly focuses on non-distributed setups, and the analysis of distributed API rate limiting through load balancers have not been explored before. Also, there is a significant gap in benchmarking and comparing the performance and accuracy of various rate limiting algorithms in distributed environments and exploring ways to further optimize them. This project aims to address these gaps by evaluating different rate limiting algorithms within load balancers using different state synchronization mechanisms and assessing ways to further optimize them for performance in distributed environments.
This slide introduces the methodology we followed for our project. It's divided into four main parts: setup, algorithm implementations, optimizations, and finally cloud setup and testing. Our system is built around Nginx, which acts as the load balancer where rate limiting algorithms are injected through Lua filters. For synchronizing request state across multiple load balancers, we explored both centralized and decentralized approaches. Centralized options include Redis and MySQL, while on the decentralized side, we evaluated CRDTs for eventual consistency without coordination overhead. All components, including load balancers, data stores, and backend services, are containerized using Docker to enable easy deployment across various environments. Additionally, JMeter is used to simulate client traffic and test the system under different load scenarios. The diagram here highlights the both synchronization strategies we investigated. For the backend, we used a microservice-based web store application called tstore. It consists of multiple services communicating via REST, which helps us simulate realistic API traffic. Its flexibility made it ideal for testing and evaluating rate limiting under different load scenarios. We implemented all 6 algorithms covered in the literature review, each with different variations. These versions differ based on the synchronization mechanisms used, specific optimizations applied, and configurable parameters like rate limits and window sizes, which are handled through script variables. At runtime, the selected algorithm is dynamically mounted into the Nginx container and executed before each API request, allowing for flexible experimentation. The diagram here shows how the framework works. All source code is open and available on GitHub for reproducibility and further testing. In high traffic situations, inconsistencies in throttling accuracy occur due to race conditions while accessing shard rate limiting state. These were mainly caused by two factors: multiple Nginx instances accessing the same data store, and concurrent worker process within a single instance accessing shared memory or Redis. To address these concurrency issues, we explored several solutions like using atomic counters, Lua scripts, and multi-execute blocks in Redis, as well as read committed transaction in MySQL. We also evaluated OpenResty logs to control access at the Nginx process level. Each of these was tested with consideration for performance and consistency trade-offs. Frequent calls to external data stores can severely impact performance, especially under high traffic or multi-region deployment where the data store becomes a bottleneck. To address this, we implemented asynchronous versions of the algorithm where load balancers only synchronize with external store during key events like quota exhaustion. We utilized the Nginx shared memory module to store the state locally within the load balancers, reducing the need for frequent external calls and improving performance. However, this introduces a trade-off between performance and accuracy in distributed setups. While asynchronous approaches improve performance, they may slightly reduce the accuracy due to the delay in synchronization. Initial development and functionality verifications were performed in a local environment, allowing us to optimize the algorithm for early stage testing. For performance and scalability evaluation, we then moved to a cloud setup on Google Cloud, simulating real-world scenarios in a single region deployment. We use E2 standard 4 virtual machine instances, each with 4 virtual CPUs and 16 GB of RAM for all nodes in the cloud setup, ensuring a robust environment for testing. The key variables in our experiments include the algorithms used in the load balancers, the state synchronization method, and the traffic pattern tested. We evaluated three main metrics. Latency measures the time it takes for a request to go from the client to the server and back. Throughput is the number of requests processed per second. Throttling deviation indicates the accuracy of rate limiting by measuring how much the system deviates from the specified request limit. Let's now go over the results, highlighting the key findings from our experiments. Our testing showed that the rate limiting framework added almost no extra latency, under 1% compared to the non-rate limited setup. Interestingly, all algorithms performed similarly in terms of latency for a given state synchronization method, indicating that theoretical differences have minimal impact on real-world performance. Among the synchronization methods, CRTT-based synchronization had the lowest latency, followed by Redis and MySQL, with only a slight increase in overhead. Throughput remained consistent across all tests, confirming that the framework handled traffic efficiently while maintaining our defined targets. We found that throttling deviation remained consistent across all algorithms, regardless of the synchronization method used, indicating similar levels of consistency. The eventual consistency model used in Redis Enterprise with CRDTs did not significantly impact throttling deviation, performing comparably to other methods. In terms of algorithm performance, sliding window lock showed the lowest deviation due to its precise timestamping, while the fixed window counter had the highest due to its rigid boundaries. Other algorithms showed moderate deviation influenced by their specific configuration parameters. The bar chart here shows the variation in throttling deviation across different algorithms and data stores. The analysis of the asynchronous versions revealed minimal latency differences compared to the standard batch quota algorithms, particularly when using Redis in a single region setup. This is due to Redis' efficient in-memory data access and negligible network overhead in a single region deployment. However, there was a slight increase in throttling deviation for the asynchronous versions, which is expected. This can be fine-tuned by adjusting the static batch percentage, offering a way to mitigate the deviation. These two images shows how the latency and throttling deviation varied between normal and asynchronous versions. In conclusion, our rate limiting framework introduced minimal performance overhead, less than 1% in latency, while maintaining stable throughput across all configurations. Sliding window lock provided the best throttling accuracy, while fixed window counter showed the highest deviation. CRTT-based synchronization proved to be the most efficient, offering the lowest latency overhead, followed by Redis, while MySQL showed higher latency due to disk-based storage access. This suggests that API providers should prioritize CRDT implementation when possible for optimal performance. For future research, we aim to explore synchronization in multi-region deployments under high load and optimize batch quota implementations through message queue integration for more efficient quota sharing between distributed load balancers. We proposed a lightweight load balancer based approach for distributed API rate limiting. Our design includes a novel asynchronous quota system and uses CRDTs for efficient and resilient synchronization. This solution is well suited for today's distributed cloud native systems, especially with API demand surging due to AI and LLM use. The entire implementation is open source and available on GitHub. It is production ready, modular, and can be easily integrated into real-world distributed system. Designed with extensibility in mind, it supports customization of rate limiting logic, synchronization backends, and traffic shaping strategies.